All right, perfect. Okay, so I'd like to welcome everybody to our third group, group number 3, I should say, for today in our chemical engineering design course. So the title of this design project is the GOCell, an enzymatic biofuel cell, and it's given by Adam, Cait, Emily, and Alyssa.
Okay, so just to get started. Hi everyone, we are Zymes Technology, and we're going to talk to you today about our product, the GOCell, an enzymatic biofuel cell. Just an overview of our presentation. First, we're going to introduce you to our team at Zymes. Then we're going to talk about the problem with battery technology today, and the solution to that problem, the GOCell. Then we'll go over the reaction equation and mass balance associated with the cell, and then we'll go over the process flow diagram associated with our manufacturing process. Then we'll talk about the detailed design of the GOCell and the safety concerns that we might have with it. And finally, we'll end up with some numbers, economics, the business plan, and why you should invest with our company. And finally, we'll acknowledge everyone that's helped us to get to this point.
So let's meet the team. I'm Cait Reiter. I'm the Chief Executive Officer of Zymes Technology. I have previous experience with project management at Teleflex.
I'm Alyssa Stavola. I'm the Chief Financial Officer due to my international business experience at Pamoja in Uganda.
I'm Adam Giusti. I'm the Chief Technical Officer, and I have experience with electrochemical synthesis and mechanical design at Pelion Technologies.
And I'm Emily Spence. I'm the Chief Safety Officer, and I have experience with environmental health and safety at ASML. And our mentor is Larry Seidler. He couldn't be here today, but he's worked over 20 years at GE and 22 years at Reiter. He's also a Six Sigma Black Belt.
So the problem with battery technology. Batteries are a non-renewable energy source. So when implanted in the body for a biomedical device, they require replacement surgery. These surgeries are invasive and can cost up to $37,000. Our solution is to have an enzymatic biofuel cell power biomedical devices. Now this is a renewable source of energy and it's completely biologically compatible within the body. However, there are some issues with current enzymatic biofuel cells today. They suffer from low power density, short enzyme lifetime, catalytic inefficiency, and low fuel utilization. We have specifically focused on improving fuel utilization in our design. So our product is the GOCell, short for the glucose oxygen fuel cell. And the GOCell uses chemical reactions between glucose, air, and enzymes to produce renewable power to power implantable medical devices. Now, glucose is a cost-effective fuel choice, and also, as I mentioned before, enzymatic biofuel cells are completely biologically compatible within the body. Our design features 3 new components, the first of these being flow-through electrodes, the second being an optimized electrode geometry, and the third being a recycle stream to improve the efficiency of our fuel cell. And here's the front view schematic of our GOCell from SolidWorks.
So I'm going to give you a brief overview of how an enzymatic biofuel cell works. There's 2 sides. There's the anode and the cathode. The anode is negatively charged and the cathode is positively charged. On the anode is the oxidation reaction and on the cathode is the reduction reaction. And the flow of electrons create electricity. So these are the equations for the GOCell. So equation 1 is on the anode, so this is the oxidation reaction. There's 2 moles of glucose reacting with glucose dehydrogenase, which is an enzyme, to create gluconolactone, 2 electrons and 2 protons. Equation 2 is on the cathode. This is the reduction reaction. This is oxygen and protons reacting with bilirubin oxidase, which is an enzyme, to create 2 molecules of water. Next, we go into the mass balance. The general form of a mass balance is in minus out plus generation minus consumption equals accumulation. In our terms, we only have an in and an out term. There's no accumulation. So next is the process flow diagram for the production of an enzymatic biofuel cell. First step is we clean the electrodes with the UV ozone cleaner. Next, it splits into 2 paths. There's an anode path and a cathode path. The first of this is the coating of the electrodes. This is a multi-step process and it's detailed in our design report, but essentially after each coating it needs to be dried. And then once this coating is completed, we move into the measurement step. So the first measurement we take is we measure the surface area and pore size of the electrodes with the Bell Sort Max. Once this is done, we see if it's a uniform coating. If it is, we move to the next step. If not, these electrodes are disposed of. The next measurement is we measure the thickness with a coolant-proof micrometer. The anode should be 2.11 millimeters and the cathode should be 0.905 millimeters. Again, if this thickness is correct, we go to the next step. If not, it's disposed of. However, I would like to note that this failure rate for the electrodes is very low because we have a great quality management system where we have great SOPs, so everything's standardized. So after we go through these measurements, we move back into the dry assembly of the fuel cell. And once this dry assembly is completed, we do a leak test with soapy water to verify that it was assembled correctly. And then lastly, we add the fuel, which is glucose, to the fuel cell.
So Zymes technology requires several pieces of equipment to power and to manufacture our GOCell. The first of these being a Bell-Sort Max gas absorption instrument, which is required to measure the surface area of our electrodes. A UV plus ozone cleaner system is needed to clean the electrodes for pre-treatment. An oven is needed to dry the electrodes after they have been treated, and a laser scanning microscope is used to check the electrodes for any impurities. A micrometer is used to measure the thickness of electrodes, while a moisture meter measures the moisture content of the cathode solution. A pH meter measures the different pHs of solution, and an Avtron load bank is required to test the fuel cells to make sure they're cycling up to performance. In addition, we need a laser cutting machine to cut the Torre paper for our optimized electrogeometry.
So now we're going to talk to you about the detailed design of the GOCell. And the first step for us in designing our GOCell was deciding what fuel to use. So enzymatic biofuel cells can run on a variety of different fuels, like many different types of sugars and also alcohols. So we researched what papers were available to us today, and we came up with 3 top contenders for our fuel system. The first being a glycerol and air fuel system, the second being a fructose and air fuel system, and the third being a glucose and air fuel system, with glycerol, fructose, and glucose on the anode and air on the cathode. So we first eliminated the choice of glycerol and air because the enzyme associated with glycerol couldn't be purchased from suppliers. We would need to make it in-house. So we decided that this would be A, too time consuming, and B, too costly for us to do. So after we eliminated that option, we compared fructose versus glucose for our anode fuel. And we found that fructose was orders of magnitude more expensive than glucose. So to keep our prices down, we ended up choosing the glucose and air fuel system. So as I just said, glucose and air are both economically feasible. For our process, you'll see later that it only accounts for a fraction of our total fuel cell price. Also, both of these are biologically compatible within the body. So the GOCell, we ultimately wanted to convert it to work in biomedical devices and run on human blood. So by using glucose as a starting fuel, we'll be able to convert it from running on glucose bought from suppliers like Sigma Aldrich to glucose running in your bloodstream. And finally, from the research that we found, glucose and air have achieved the highest power density out of any other fuel, which is important because we want to make the most power in the smallest amount of space. So after we found our fuel system, we then needed to pick which enzymes we wanted to use to make our reaction happen. And we ended up choosing glucose dehydrogenase on the anode and bilirubin oxidase on the cathode, as Cait had said. But you can see in figure 3, those aren't the only enzymes we're using. We're actually using a multi-enzyme cascade system, which allows for mediated electron transfer. So how that works is that your fuel flows over your electrode on the outermost part and reacts, and then your enzyme, or your electron, is shuttled from enzyme to enzyme all the way down to our current collector, and that's what makes electricity. And this adds to our power density. Also, as I said before, we were concerned about being able to purchase all these enzymes from suppliers, and luckily all of these enzymes, we don't need to make them in-house, we can buy them. And finally, as Cait said, we're using a novel coating process to immobilize our enzymes on the electrodes, which adds to the stability of our fuel cell.
So as we previously mentioned, our main goal was to improve the fuel utilization of our cell. And we took a few novel approaches to this, and the first and foremost was we used flow-through electrodes. And this is where we took our glucose flow and we floated up through a turbulent flow exchanger, which is these anode discs. And these anode discs are aligned in such a alternating ABA pattern. So it'll flow up in kind of a jigsaw pattern. Flow up, kind of swirl, and go over and up. And the whole point of this is we want to promote as much turbulent flow as possible. Normally, in a standard fuel cell, your fuel will just flow up against your anode. And this leaves little mixing, and there can be some empty active sites. So we wanted to avoid this. So with turbulent flow, we got as much mixing, and we kept the number of active sites unoccupied to a minimum. And this is all over. Our anode disc is a Torre carbon fiber cloth, and as Emily previously noted, there are mobilized enzymes all over this. And another big draw to this is, in a standard fuel cell, you just flow over one side. We're using a series stacked, so we'll flow against both sides, so we'll have immensely greater surface area of reactivity. And another way we optimized our anode disc was we used specific electrode geometry. And you can see here some charts of a study of various geometries and how that affects edge effects. Edge effects in a cell affect the resistive heating and the current density distribution. So with an elliptical shape, you have a very low current density distribution, which is preferable for a more even reaction rate. And it also keeps the resistive heating towards the low side. It's not the lowest, but for us it was the most practical one. Next, you can see our size is fairly small. I know it might be a little hard for people who aren't familiar with metric, but it's about 1.5 cubic inches, which is pretty small, but we want to bring this down even further because we want to put this ultimately in the human body. And in case of catastrophic failure, the smaller it is, least likely we are to cause any blockages or any disruptions within your body. Next, we're going to make use of a recycle stream. And this hasn't been done before much in fuel cells because the fuel has been, as far as most people have seen, it's been cheaper, but since we want to use the body, we want to get as most utilization out of our fuel as possible so we can get a higher voltage and a higher current going to power our device. So this is where we stack. On the next page, I'll show you an actual diagram of this, but we stack our cells on top of each other, and they flow up into the exchangers, and any unspent fuel will flow up into the next cell, and then so on and so forth. So you can see here, blue is the piping where the glucose flows, and you can kind of see that gray silhouetted line. That just shows the overall flow that's hidden. So it flows up, and it splits into a T, and it goes up into two different exchangers, comes back, meets up, and goes into the next cell. The black is our anode, red would be the cathode, and the white are spacers, so we can stack the cells on top of each other. And on the bottom of the red, the cathode, is where the air flows up and will interact with the hydrogen protons and create water on the bottom of that. It's important to note that the glucose and the air never actually physically meet. All the electronic interchange happens in the anode, and the protons flow down to meet with the air. So here's a two-dimensional schematic of how our flow actually works. So you have glucose in the air operating from the bottom. The glucose will flow up over the cathode plate, up into the anode exchanger, and flow over and up into the next cell. And this is a SolidWorks assembly of how our entire stack will actually play out. So you can see, if you follow the gray little silhouette lines, how they flow up, split, come back, and then go on to the next cell, and so on. And again, this is just to get that recycle stream going. And these are flowing in series, but the way we plan to wire these is in parallel. So the flows in series is very independent of how we're wiring them. We're wiring them in parallel to get a higher voltage. And this will allow us to operate a greater deal of devices. And on the bottom, you see this larger plate, that is our cathode plate. And this cathode plate is porous, it has some square notches cut out so that air can flow up onto the cathode and react. And as you can see, the spacers are intentionally designed, it might be hard to see, but air can actually flow through those subsequent cathodes to react as well. And again, we plan on bringing down the overall size of this, but this model actually works out very well from a research perspective. We're not as concerned about the optimization yet. We're more focusing still on our chemistry. And the top plate is aptly named the anode plate because it's covering the anode.
So after we completed our design of the GOCell, we then needed to look at safety because Zymes' ultimate purpose is to keep, first of all, workers safe, but then once we send this product to market, we need to keep our customers safe. So the first step in our safety analysis was a material review of all the chemicals that we're going to be using in the manufacturing of the GOCell. So I've only included the materials in Table 2 that are hazardous. We have a lot more that aren't listed here. They're in our report, but those are mostly enzymes that aren't concerning to our workers or the human body. So first thing I'd like to point out is that 4 of the 5 of these chemicals have toxicity ratings. So VK3, PBS, acetone, and potassium ferrocyanide. So they have toxicity ratings in mice, so unfortunately we won't be able to tap the implantable device market for mice, but for humans, we are looking pretty good because these are toxicity class 4, which means they're practically non-toxic to humans. And we're also using them in low amounts. So you can also see in the second column, NADH has a stability rating of 1, which means it's going to react with water if it comes in contact with it. And although this won't be a violent reaction, we still want to make sure it's stored away from any water, and when it's used in our coating process, make sure it's not used near water at all. And then you can see an acetone column. That's one of the most dangerous chemicals that we're using because it does have an explosivity rating in air of 2.6 to 12.8%. So we're going to make sure this is stored away from any ignition sources and also used away from any ignition sources when we're making the fuel cell. And I also want to point out that none of the chemicals that we're using have a corrosion rating of greater than 1, which means they're non-corrosive. So our fuel cell components don't need to be corrosion resistant. And just as a general precaution, we're going to make sure everyone that will ever come into the lab will have proper safety training for chemicals, and they'll also wear personal protective equipment like goggles, gloves, and lab coats, and we're going to also have eye wash stations and showers, just in case anybody does have a safety accident. So after we did our material review, we went on to do a failure mode effect analysis. And to do a failure mode effect analysis, we looked at each process step for making the GOCell, and we brainstormed anything that could go wrong with that step. After that, we looked at the severity, if that problem were to happen, the occurrence, so how often it might happen, and also our current detection limit to see if we needed to take extra action than what we're doing now. So I listed the failure modes that needed extra action to be taken in this table. So our first process step is the electrode coating, and a failure mode that could happen with that process step is an incorrect concentration of enzymes on our electrodes. So the consequence there would be a decreased reaction rate with our GOCell. So as Cait said before, our action is going to be a thorough quality analysis of all of the electrodes before we put them into our fuel cell. So we're going to test the surface area with the Bell Sort Max, test the thickness with micrometer, and we're also going to look with the laser scanning microscope to see if there are any impurities on the electrodes. And we're hoping that this failure rate will be low because of training and thorough SFPs. The next failure mode is a missing part in our dry assembly process step. So this could create big problems because if an electrode was left out, you're not going to have any reaction in your GOCell. Or something smaller like a separator was left out, we could have crushing of our fuel cell, and that's not something we want to happen. It won't work that way. So our action here is a redundant check of fuel cell builds. We're going to have everyone trained on how to build fuel cells, but before we test them, we're going to have multiple lab techs and managers check to make sure all the parts are there before we bolt it together and test it to prevent anything bad from happening. And then our last process step is the actual powering of our enzymatic biofuel cell. And there are two failure modes here. So the first one is an interruption of reactant flow, either glucose or air, in our fuel cell. And this would ultimately make our GOCell not work. So we're going to add flow and pressure meters to all of our inlet streams to make sure that we're flowing properly into the fuel cell. On the other end, we're going to, we predicted that maybe waste buildup would be a failure mode going out of the fuel cell, which could create an unsafe pressure within the cell. So we're going to have a check valve on the outlet streams, and a check valve basically prevents backflow from waste flowing out of our waste catchment system back into our fuel cell to prevent that from happening. So the last safety analysis that we did was a hazard operability study. And what we did here, we looked at just the streams flowing in and out of the fuel cell. And we used these guide words all the way to the left here to predict anything that could go wrong with those streams. And then we took action if we thought that we didn't have the proper safety measures available to us yet. So I only included 2 here. We have many more in our report, but this is stream 1, which is the feed of raw glucose to our fuel cell. So as I said before, the main problem here is going to be improper flow. So it's either no flow into our fuel cell, we're not going to have any reaction. But if, on the other hand, if there's too much flow, then we could have an unsafe pressure. So in addition to the pressure and flow meters on our inlet streams, we're also going to have a process control system with alarms. So if any flow or pressure is outside of our specifications, it's going to alarm and possibly e-stop to prevent a catastrophic failure from happening. Also, heat is concerning to us here. We need to have the proper heating of glucose in our feed stream, because if glucose is too cold, then it's going to be viscous and clog up our cell. So we're also going to have thermocouples placed around the fuel cell. And finally, we want to make sure we have the proper feed concentration or composition in our fuel cell. We're running the GOCell on 0.4 molars glucose and phosphate buffer solution. So if the concentration isn't correct, our predicted reaction rate won't happen. So we're going to first have everyone trained on how to make our feed solution, but we're also going to test batches of our feed before they enter the GOCell to make sure we're meeting our specifications. And here's the other hazard operability study that I'll talk about today, and this is for stream 4, which is the removal of gluconolactone waste from the fuel cell. This is just gluconolactone, not water. So problem here would be flow. If we don't get flow out of the fuel cell for some reason, clogged waste port, something like that, it could result in an unsafe pressure and the fuel cell could explode, which would hurt our employees. So not only will we have flow meters on the inlet, we're also going to make sure we have flow meters on the outlet streams to make sure we have a steady state flow through the fuel cell over time. And the other problem that we have for the removal of gluconolactone is composition. We want to make sure we're only removing gluconolactone and water from the fuel cell, not glucose and not air, because this will decrease our reaction rate. So right now we have proposed a two-step waste removal process. We're going to have two waste ports. One is going to have a membrane filter with a pore size of about 0.3 nanometers, which is slightly larger than a water molecule. So that port will only remove water. And we're going to have another waste port with a membrane with a size of about 1.5 nanometers, which is a little bit smaller than glucose, but a tiny bit bigger than gluconolactone. So hopefully we'll be able to remove gluconolactone and water from that waste port. But Zymes Technology needs to do more research and testing with our waste removal techniques, but this is our initial proposal.
So now on to the economics portion of our presentation. Our market analysis shows that the U.S. implantable medical device market is going to increase at an average rate of 8% per year and is going to reach $73.9 billion by 2018. This figure shows the market growth for the implantable medical device market. There are many different potential applications for our enzymatic biofuel cell. These include pacemakers, defibrillators, drug delivering pumps, blood glucose monitors, sensor transmitters, and neurostimulators. And we also looked into potential customers who would purchase our enzymatic biofuel cell. And we looked into 4 large suppliers of biomedical devices. And these are Biotronic, Medtronic, St. Jude Medical, and Abbott Laboratory.
So now I'm going to give you some numbers on why the novel research being done at Zymes Technology is a great investment. So to start out, we chose Research Triangle Park in North Carolina as the location for Zymes Technology. It is one of the leading research and development centers in the U.S. with 3 of the major research universities nearby, Duke University, North Carolina State University, and the University of Carolina. So we chose specifically the lab in RTP. The base rent for office space there is about $16 per square foot per year, and the base rent for lab space is $21 per square foot per year. And this base rent includes janitorial services, utilities, building and ground maintenances. So in Table 6, this is a breakdown of the numbers that the rent's going to cost for Zymes Technology. We went with 500 square feet for office space and 500 square feet for lab space. This totals to less than $20,000 of rent per year. I know this seems significantly cheaper, especially us being in Boston, but North Carolina has a cheaper living expenses, and then also RTP is trying to promote the research and development community there. So we want to be a part of this community, and also there's going to be great resources for our research there. Next is the operating and utility costs. So as I said before, the utility cost is included in the base rent at the lab. And the positions within Zymes Technology will be, the salaries for these positions are operating costs. So we're going to have 4 managers, 3 laboratory technicians, and 1 co-op. And each of these positions will be working 40 hours a week. So the total operating cost is $600,000 per year. Next is the installed capital costs. So in this table is all the equipment that Alyssa has already detailed out for us, in addition to the installation cost to install this equipment that's needed to produce our enzymatic biofuel cells. So the total installed capital cost is $153,514. And then lastly, we needed to calculate our raw materials cost. So we have the fuel and enzyme cost. So the fuel is the glucose, as Emily stated before. And then both the anode and the cathode are coated with enzymes. And this total for fuel and enzyme is about $1,400, and this is per fuel cell. And then on the other side, we have the fuel cell components. So this is the electrodes, the silicone gaskets, titanium mesh sheets, and plates, and the current collectors. And this is less than $6. So as you can see, our major cost is the enzymes. And we plan in the future to reduce this cost by looking into synthesizing these enzymes. But in total, one fuel cell, to produce one fuel cell, it costs us $1,405. And Zymes Technology is going to be selling it for $2,500.
So we mocked up a preliminary business plan to get us through the first fiscal year. So right away when we start up our company, we're going to break off into 2 teams, 2 of us apiece actually. And first we're going to have a mechanical team that'll focus on stability improvements and mobilization techniques, longevity improvements. And their overall purpose is to improve the stability and lifetime of our fuel cell. And next is the electrochemical team, which will focus on improving our energy density and our fuel composition. So they're going to focus on experimenting with different enzyme fuel combinations and improving the overall electrochemistry of our cell. Next, in the short term, we're going to make a few key hires. First and foremost is the computational modeling expert. They're going to assist with modeling and analysis of fuel enzyme combinations, because there are hundreds of combinations that we could potentially use. So if we get a good modeling expert in here, we can eliminate a great deal of money wasted on screening all of these various compounds, because you've seen how expensive those enzymes can be. So in the early stages, utilizing this person, they'll save us a great deal of time and money, and it'll give us a good direction to start our company off. Next, we'll be hiring 3 technicians, and they're going to execute on the builds that we, the leads, come up with. So this will free us up to come up with more experiments, and in turn, we're going to be hiring more technicians to free us up. So basically, we're going to improve our throughput. Next, we're going to have an accountant who will handle all things money. They will handle our taxes, our payroll, and they'll be taking care of all equipment procurement. Basically, if it needs a dollar sign behind it, this guy's on it. Next, our long-term hires. We're going to be hiring a business expert. This person will be taking over. Once we get into the area, we have a product that's somewhat marketable. This person's going to come in and start directing the company. This person's going to have to be very technically savvy, and they're going to have to know where to push our research, where our product would actually fit in the market. So this person is going to be taking us, directing our company, negotiating with other companies for additional investments, and handling eventually all of our sales and licensing. And also, as we go on, if we find any niche problems that we're having, where we need to hire any additional chemists and engineers, or if we just need more people to lighten the workload, we'll hire them as we go. So here's a general timeline we've worked out for that first fiscal year. So in the first month, we'll be securing our initial investments and starting to set up all of our equipment in our facility. And by the beginning of the second month, we want to have all of our equipment up and running. We want to have a functional lab. And by the third month, we want to have our fabrication processes and our SOPs written out. So we're going to start standardizing all of our processes. And here, this is where we're going to start working up all of our builds. And this is where we're going to start collecting baseline data. And this baseline data is going to be very important going forward. For this baseline data, we're going to use more established fuel cell compositions. And this is just so we can get background data for all of our experiments. So if anything goes wrong if anything's different about our baseline data of the same fuel cell 6 months from now, we know something's contaminated in our lab or something's happened with our process. And this just allows us to mitigate any issues with that. Next, we're going to have around 4-month mark. We want to be about 10 cells a week, and we're going to be hiring on our technicians, so we're going to be ramping up this cell amount. And eventually by 6 months, we want to have all of our technicians, our accountant, and our modeling expert hired, and this is where we can kind of get into full swing, full steam forward. Around month 11, we'll be fundraising. We're going to look back at our previous fiscal year, see how we spent our money, see what we need to raise going forward. And at the end of the year, we're going to do a meta-analysis. We're going to look back, see all of our experiments, see where we spent, see where we could pick up more efficiency, and this is just so we can spend your money better. We want to be as efficient as possible. We want to work up our product as quick as possible, and this just allows us to look back and just do a self-review. And then, jump forward, month 18, about a year and a half in, we want to start headhunting for that business lead I was talking about previously. This is the person who will, again, from here going forward, they're going to be directing our company. We want to be competitive and we want to get to the market as quick as possible, but we want to be safe while we do it. So this person's going to be savvy, safe.
So, why you should invest in Zymes technology. As I mentioned previously, the market is going to continue to expand aggressively, which makes it a great market to enter into. Also, we have a breakthrough technology. We believe that enzymatic biofuel cells will replace batteries in implantable medical devices. We also have a company-wide sustainability policy. The GOCell produces no carbon footprint and also utilizes environmentally friendly waste disposal methods. We plan to ramp up production to 200 GOCells per year to produce a profit, and we only require $3.2 million in investment for the first 5 years. We have calculated that we will break even in 7 years with a net present value of $900,000, and our internal rate of return after 10 years is 32.6%. So not only do we have environmentally friendly product, but we also have a financially sustainable business model, and that's why you should invest in Zymes Technologies. So we'd like to thank both of our professors, Professor ChE and Professor Webster, for their time and encouragement with our project. And we'd also like to thank the Chemical Engineering Department for the resources and funding allowing us to take our Capstone research one step further. And unfortunately, our mentor couldn't be here today, but we'd like to thank Larry Seidler for his sound advice and constructive criticism, challenging us to delve deeper into our research, and also for his availability to commute into Boston so many times for so many meetings. Thank you. Any questions?
Questions?
I've got a question. Have you looked into what technology is available to be able to deliver the glucose in the air to the fuel cell while in the body?
So we were looking at putting this in the body is more down the line. This is what we ultimately aim to. Right now, we're focusing on improving a fuel cell to that point, but we plan on utilizing blood oxygen and blood glucose, and that's something that we're going to work out during research. There isn't as much research on how to do that right now. That's not something that's really been played around with as much.
Right. Yeah, it was clear that this was more about creating this particular fuel cell, but if your overall aim is to use them to replace batteries in the body, I'm wondering if you saw anything in the market that actually extracts the glucose in the air.
There is already on the market a blood glucose monitor that uses
Enzymatic
fuel cell, and it pulls off some of the glucose from there, and it uses air from that atmosphere.
Technology.
So that's a proof of concept already out there, and we just want to bring that one step further and actually bring that in the body.
So that could be easily incorporated into your device. So, but it is pulling the glucose out of liquid,
Yes.
though, not air, right?
Right, yeah. It would be your glucose in your blood.
Yeah,
So that's
yeah.
how that device works by, I'm assuming, prick your finger, and then that's how it powers the entire thing.
Yeah.
So that's
I
what
I was actually thinking, just to continue along that thought, that, for people who have diabetes, right?
Yeah.
Type 2 diabetes is skyrocketing.
Mhm.
Could this serve as a way to metabolize glucose for those patients who are unable to metabolize glucose? You're basically creating a way in which you can consume glucose.
Right, exactly. So that could be an additional benefit to that. So we're not only looking at pacemakers, but yeah, we're looking at a bunch of different ways that we can incorporate this into different biomed devices just running on blood. So that's definitely a possibility as well.
My only other question, I think you guys did a fabulous job, that's why I don't have many questions, is the interaction of, and I think you touched upon this a little bit in your HAZOP analysis, but the interaction of glucose with the fuel cell. And especially if you're creating turbulent flow, if you're creating alternating flow environments, that interaction could be more problematic.
Right.
In which you have disruption of flows, you have subtraction of glucose onto the device itself rather than utilizing it as a fuel. So I don't know if you could comment a little bit on the expected lifetime of this device. Would the failure mode of the device be the buildup of glucose in the chambers?
So the lifetime of enzymatic biofuel cells at this point is pretty low. So that's another one of our targets, is to make it last longer. And yeah, you're right. The anode reaction is the limiting reaction here. But I think the problem would be not so much glucose, but the enzymes actually not having the lifetime, because with this reaction, you actually don't take out all the electrons from glucose when you react with it one time. That's why we're using the recycle stream. So, I mean, yeah, glucose is a concern. We're hoping to mitigate any unreacted things with the turbulent flow, but another concern is going to be our enzymes in the future, being able to last and get the full reactivity out of that.
So on the vein of the turbulent flow, we actually have a lot of play with our discs. We actually have some discs on the table.
Yeah.
I forgot about these.
Yeah, so we actually have a lot of play with that. We can experiment a lot with our hole size on the center of the holes, and the more we expand those, the less turbulent flow we'll have, and we can get, if you actually expand them in an alternating pattern, end up with a little bit of an overlap where you can get straight flow through. So that's something we'll play around with in the future. And if we experience reduced flow, then we have a solution to that already available. And that'll still create enough mixing. That's something we need to experiment with. We already have that in our mind for research, but.
Good. Did you mention how you made these? Do you want to mention how you made them?
So yeah, these were 3D printed using the Studio.
That's the end plate.
Yeah.
Unfortunately,
This is the anode disc.
we have such a small scale of our enzymatic biofuel cell that we actually had it printed a few times, but it was very small and very fragile that I don't think our printing lab was experienced enough to handle that.
Yeah.
So it was
So we just
cost
have the
effective.
components.
Yeah. So yeah, we have those. I mean, I can pass them around. So yeah,
It's
you,
about like 2/3 the size of the
so
the
it's,
printed material of
Yes.
what the size of our actual enzymatic biofuel cell is.
and if you like lay the anodes over each other, you can twist and turn it to get that exchange pattern. And that's what we want to do.
Great.
Yep.
So even if we're at about, you said 2/3 of the size of this right now, it's still a pretty large thing to be putting, like you said, mentioned in your presentation. What kind of problems do you expect to encounter when you get to sizing this down to more applicable size?
So something off the bat I know we can do is there's a lot of dead space, if you noticed, at that assembly stack. There's a lot of open area that doesn't need to be open to the air. So going forward, like I said, that's just a research model. We want to make that as simple as possible so we can conduct our research without worrying about other variables. And as we actually bring our research, bring it all down the scale, we can close those gaps, make our piping a little bit more optimized. So going forward, that'll be something we'll handle later on. For now, this is a good model for us for research, and we'll kind of take that as it comes.
And also, our dimensions right now, the length and width of the fuel cell is okay. It's a little bit smaller than pacemaker, I believe, but the thickness is the issue too. So that's going to be like one of our main targets, is to reduce the thickness of the fuel cell to make it in like a, not paper thin, but pretty thin pacemaker if we want to attack that market.
Excellent. Well, we should move on. Thank you very
Yeah.
much, GOCell.
Thank
I'm
you.
ready to write a check.
Ready to go?
Thank you.
Thank you.
Thanks.